In this video, we're going to be looking at solving for support reactions, but in 3D now. So we're doing equilibrium of a rigid body in 3 dimensions, which means that we have 6 possible equilibrium equations that we're going to be using and applying to find these support reactions. So it's the sum of our forces in the x, y, and z directions gives us 3 equilibrium equations for force, and then we have 3 equilibrium equations for moment, each about the x-axis, y-axis, and z-axis, giving us our 6 equilibrium equations that we're going to be using in the following examples. So let's take a look at how we would apply these equations. So in this first example, we're going to be finding the support reactions at A, B, and C. So A, B, and C all have the same type of support. They're all pinned, right? So all of them are going to have the same type of support. It's just the direction they face may be slightly different. So of course our first step is going to be our free body diagram, which I'm just going to go ahead and do this line along the Y, then it turns along the X and goes down in the Z. I'll just leave it as a line so that I can see it for now. And then I have this 400 Newton force in the y-axis direction, 600 Newton force in the z-axis direction, and then I have my support reactions. So here I've got AX support and an AZ support. Since the rod is along the y-axis, I only have the other 2 supports and not the y support. Then for my B, I have a BX and a BZ. Notice these are the same, but I drew them in different directions for no other reason than I thought it was more convenient to draw them that way. We'll figure out whether I drew them right or not when we get to the end. Again, the math is going to work it all out to see whether these are positive or negative, and if we get the right answer at the end. Right? The answer will always come out correct. It'll fix all of your signs. And now for C, it's oriented different than the pins at A and B. So for C, we actually don't have a force in the Z direction, but now instead in the Y direction and the X direction. Oh, sorry, this is C, not A. Y direction and the X direction on C. So I have 6 unknowns, 6 reactions. So this is a stable system, right? Because I need 6 reactions for it to be stable. And I'm going to need to solve for all of these. Now, this is the tricky part, right? With 6 reactions, we have to apply 6 equations. And where do you even start with that? So my helpful, I guess, tip is try to see if you can see anything first. And what I mean by that is, like, in this case, there are only 2 forces acting in the y directions. Cy, and let me highlight them, are 400 Newton force, and Cy are the only 2 that are acting in the y direction. Every other force is either a z or an x, and there's no applied moments. So I might, in this case, start with my Fy reaction, because if I do sum of forces in the y direction equals 0, I'm going to have 400 minus Cy equals 0. And I can find that my y reaction at C is just 400. And that we had assumed the direction correctly, right? It's exactly opposite in direction from the 400 newtons. So I'll indicate that my direction was correct here, that it is pointing in the negative y direction. So that's one way to start. Say, all right, I looked around. If I look at my x's, I have 3 unknown x's. If I look at my z's, I've got 2 unknown z's. So I maybe don't want to start with those force equations. I don't want to start with those equilibrium equations for fx or fz. But fy, I've already got one answer. So then we'd move on to be like, okay, which of the moment equations do I want to start with? Remember, in these, we aren't taking a moment about a certain point, but instead about each of the three axes, right? So your x-axis, your y-axis, or your z-axis. We're going to take moments about each of them. And the question is which one to start with, right? You can start with any of them, but I personally would probably start with my x-axis in this case, because if I take my moment about my x, remember when we take the moment about an axis, anything that is parallel to the axis or its a line of action intersects the axis does not get accounted for in our moment equation. So if I take my moment about this x-axis here, then I'm not including ax or az. I'm not including, I'll mark them. I'm not including ax or az. I'm not including bx because it's parallel. I'm not including the 400 because its line of action intersects my x-axis here. So I'm not including that one. And I'm not including cx. So I only have the bz, the 600, and the cy. And I already solved for my cy, right? So now I only have one unknown in this equation when I set up my moment. So if I take a moment, the moment about the x-axis, I assume right-hand rule is positive here. Taking the moment about the x-axis, it's going to be bz, and now bz is acting in the clockwise direction around x, so it's a negative bz times its distance away, which was 0.6 as indicated over here. So negative bz times 0.6. Then I have my 600 Newton force, which is a plus because it's acting counterclockwise around the x-axis. 600 times this distance, which is 1.2 meters. And then finally I have my cy component, and that is acting clockwise around the x-axis, so that'll be a minus as well. So minus cy was 400, we found out. And that distance is this distance here, right? From the x-axis down, it is 0.4 meters. So now I can plug that all in, and I can find out that my bz is going to be 1467 newtons, right? If I plug all that into my calculator and solve, I get 1467 newtons, a positive direction, so the direction I assumed was correct. It is acting down in the z direction. Now again, you don't necessarily need to add these arrows, add these in, right? It's already as written in our drawing, right? So I could write negative bz, I could leave it as is, really. I'd leave it as is. I found cy, I found bz. The next easiest one to tackle would be either taking another moment, or at this point, I say, okay, my z's, I go ahead, I go ahead and delete that. I found two of my reactions. I'm gonna put them over here for safekeeping. We found cy was negative 400, bz was 1467 newtons. So now that I have bz, if I look at my z components again and do summation fz equals 0, I get az minus bz plus 600 equals 0, right? So now I can find that my az is negative 2067. Negative 2067 newtons. Right, easy enough. Just doing our z summation, solving for az because we know what bz is. I'm gonna move him, keep him for make you smaller. Come over here. So I have half of my support reactions now, and so we'll just keep going through our equilibrium equations to find these. So the equilibrium equations we have left, we have not done the x's yet, but we also don't know any of the x's. Ax, bx, and cx are all unknowns. So we probably want to save that one for last, our summation of x forces. But we can do our moments, right? So let's go ahead and do the moment. Some of my moments about the y-axis now. So if I'm doing these about the y-axis, it's not going to include my 400 because that already goes through it. These two both intersect the y-axis as well as these two. So the only ones that I have left are going to be my 600 Newton force here, not my cy, but also my cx. So my cx is going to be, or my moment summation, I should say, is going to be this 600 Newton force, this guy here, multiplied by the distance away, which we said is 0.6, as indicated over here. And note that is actually going clockwise, so this should be negative. Right, and then we have our cx, and this distance here is 0.4, so it's 0.4 times cx. And note that this is also in the wrong direction. This is in the negative x direction. So when I do the math on this, my cx value comes out to be negative 900 newtons. Negative 900 newtons. Whew, almost there. Just one more moment equation to apply and one more force equation to apply. So I did my moment about y. I can do my moment about z. So if I'm taking my moment about z, these two will not be incorporated as they both go through. BZ is not incorporated, but we're going to include BX. BX will be included, and this 400 Newton will be included. 600 won't, and CX will also be included. So our moment, oops, not force. Sum of our moments about the z-axis equals 0. We're going to have bx times 0.6, right? That's the distance away from our z-axis here. Minus cx times 1.2 minus 400 times 0.4. And we know what cx is. We just found it right here. So bx is going to be negative 2067 newtons. All right, that leaves us with just one more thing to find, and that is our AX. So if I take my final equation that we haven't used, sum of forces in the x direction equals 0 it's just going to be that AX, or negative AX, I should say, negative AX plus BX minus CX, just based on signs of where they're at. And so when I plug those in, I get my AX value, it's 2967 newtons. That's it. I say that's it. It was a lot of work. It's a lot of equations. It's a lot of keeping track of where your different reactions are and finding the moments. So they are long and complicated problems. But again, it's just those summations. You're just adding things together. The tricky part is really the setup of these equations. If you can set up all 6 of your equilibrium equations, you've done probably 90% of what I would consider is the correct work, right? If you can set up the equations, that's 90% of the hard part. The rest is just calculator. It's just algebra. So getting those setups is what's really, really crucial in solving these problems. Otherwise, one mistake will carry through to everything. Let's do another example. In this example, we have a boom that's used to support this flower pot that's also being held up by these 2 cables from A to C and A to B. So let's draw our free body diagram first. So here I'm going to draw it for the body of the boom. Body of the boom is along the y-axis here, and it tells me that my flower pot is 75 pounds. I have a 75-pound force acting down on it. It didn't mention a weight of the boom, so we're going to assume that it is not contributing. And then, of course, we have the tension in these cables. The tension in cable AC and the tension in cable AB. And then finally, if we look at point O over here, we have this connection that is another ball and socket connection. So a ball and socket constricts all of the forces. So we have a Z force reaction. I'm going to call this OZ since it's about point O. OZ, a Y force reaction, OY, and an X force reaction, OX. So this is my complete free body diagram. This is all of the forces acting on this boom pole here. But this setup requires one kind of trick from our past problem solving that we've learned and worked with a lot, which is we're going to need to split up these tension components to have X, Y, and Z components so that we can put them into the Fx, Fy, and Fz equations. And if you recall how we do that, we have to make position vectors from AB and for AC, and then convert those to unit vectors and multiply by the force, right? So we're going to need our position vectors for AC and AB, then make those into unit vectors, and then of course find that tension vector as a force in Cartesian form. So we'll go ahead and we'll look at this for AC, right? So our AC, my X component from A up to C up here, right? From A to C, the X component goes back by 2 feet. So that is a -2. I'm going to put these in brackets for now. -2 for my X. Then my Y is going from 6 to 0. So this will be a 6. Or sorry, -6. Sorry. Going from a +6 to a 0, so 0 minus 6 is -6. And then finally we are going from 0 up to 3. So this will be 3. And to convert that into my unit vector, I do the position vector divided by the magnitude, right? 2 squared plus 6 squared is 3 squared, right? Position vector over its magnitude, that gives me the unit vector. And so then I multiply TAC times the unit vector. And this unit vector, when I multiply it out, is -2/7, -6/7, and 3/7. Now you'll notice that my position vector for AB is going to be extremely similar, right? The only difference is a sign flip for the x component, right? Instead of a -2, this one is now a +2. So my TAB, I can take a shortcut and just say, okay, just the sign has flipped. So my TAB vector is going to be a +2/7, -6/7, and 3/7. So now I have my components for each of these that I can plug into my equations, right? So when I set up my, my equilibrium equation for the force in the x direction, I'm going to say, okay, well, my x component of TAC is going to be -2/7 TAC, right? So we're again using those ratio relationships to solve force equations, just as we did in equilibrium of a particle. Same concept, now it's just that we have more equations to set up and solve. So if I have these two equations now, I can set up all of my equilibrium equations if I want to, right? So my sum of forces in the x direction equals 0 equals -2/7 TAC plus 2/7 TAB plus OX, right? Those are all of my x forces. And then I'm just going to go ahead and set up everything and look and see what I can solve, because this one's not quite as straightforward as to knowing what you can solve, if there's anything you can solve right off the bat. Sometimes you just need to set up all of your equations and work from there. If I do some of my y forces, I will get, let me do this in a different color so I can differentiate these. Oops. Sum of all of my y forces is 0, is going to be -6/7 TAC minus 6/7 TAB plus OY, right? The y component of my force in the ball and socket. And then finally, I have sum of forces in the z direction. I'm going to have my 3/7 TAC plus 3/7 TAB plus OZ minus the 75. So, right, the 75-pound flower pot is included in the z direction. So don't forget the -75 in our z components. So we've got all of these equilibrium equations set up, and everything has way too many unknowns, right? I've got 5 unknowns still amongst these 3 equations, so I'm going to have my moment equations set up so that I can actually solve for any of these variables. So I'm going to go ahead and I'm just going to write all of those out as well and see if there's anything that jumps out, see if there's anything that I can solve for. So let's just go down the line, right? If I take the sum of my moments about x, I'm going to get about the x-axis here, I will have the TC components, these z-TC components, because the y and the x ones either have a line of action that intersects, the y ones intersect, or are parallel, right? The x ones are parallel. So it's only going to be my z components of TAB and TAC. So I have my z component of TAC times the distance away, which is the 6 feet, right? Times 6. And it is going counterclockwise, right? These point up in the z direction. So our z components here is the 6 feet away, and it will be counterclockwise around this x-axis. Plus 3/7 TAC, plus 3/7 TAB, again times that 6, same location. And then, of course, we want to include the 75 pounds, right? Minus, since it's in the opposite direction, 75 times 6. Continue setting up my equations. Go down to the next one. Sum of my moments in the y direction equals 0. Now, sum of my moments in the y direction is very interesting for this one because the rod is along the y-axis, which actually means there is no equation for the taking the moments about y, because everything is either along the y-axis, along the line of action that intersects the y-axis, or is the y-axis, right? So there is no moment. This is it. This is the moment equation. No, none of these components are applicable. You can't take a moment. So our final equation here that we can set up is sum of moments in the z direction equals 0. And so those, right, here's my z-axis here. Those are going to be my x components, right? So nothing about my O points here, but my x components kind of face out this way and this way. So my x components of my two tensions here, 2/7 TAC times the 6 feet away minus 2/7 TAB times the 6 feet away that they're acting. Now this is an interesting one, right? This is an interesting equation that we've just set up because we can solve this in a sense, right? If we set this equal to each other, what we're going to see is that TAC equals TAB. And knowing that piece of information, we can simplify a lot of things down. For example, we can come back to this moment equation here, right? If I come back to my equation in green, now I say, okay, if TAC and TAB are equal, I can solve for what that is using the moment equation, right? So I can plug this into my calculator and I can just call both of these T. I'll just call them both T now. And I can solve this for T. So I plug that into my calculator and I get the T value, TAC and TAB equal 87.5 pounds. 87.5 pounds. And interestingly enough, I'm done, right? This problem didn't actually ask me to solve for any of the reactions at point O. It said determine the tension in cables A, B, and AC. And since they're equal and we found the tension, it's 87.5 pounds. That's it. That's the answer, right? The tension in cable AB is 87.5 pounds. The tension in cable AC is 87.5 pounds. I don't have to go and backtrack through any of these other little equations, of these little candy corn equations that I've got set up on the side. I only need that 87.5 pounds. All done. In this final example, we're looking at a plate that has 3 cables attached to it. These cables are attached up to the ceiling. There are 3 tensions from these cables, and it's asking us to find the tension in each one of them. But note it also tells us that the plate has a weight that we're going to have to account for. So let's go ahead and draw our free body diagram for this system. We have this plate. It's not sitting on anything. It's only supported by each of these cables. I'm going to call that the tension in cable A, the tension in cable C, and the tension in cable B. So now there's also this 200-pound applied force halfway between A and C. And then there's also the weight of the plate. which says it's uniformly distributed, so it's going to be in the center of this plate. In the very center of this plate, we have this weight W, this 500-pound force. And now this is a really interesting problem because we can immediately see some of the problems that we're going to have. For example, our force equilibrium equations, right? We can go ahead and set up those three, but we're going to notice immediately the first two, if we add our x components together, x forces, there are no x forces, so it's just 0, right? Same with our y. Here we only have z forces acting on this plate. So we can set up this equilibrium equation, TA plus TB plus TC minus 500 minus 200 equals 0. So that's our FZ, right? And then we're also going to find the same problems when we start taking the moments, right? When we take the moment about the z-axis, since everything is parallel to z, the sum of moments about z is again just 0. There are none. So half of our equilibrium equations are already out of the picture, and now we only have to set up our last two. Right, so let's take a look at our moment about the x-axis here is 0. And so for our moment about the x-axis, we're going to have our 500-pound force, which is acting halfway into the plate, so 1.5 feet into the plate away from the x-axis. So we're going to have that 500-pound force, 500, and it's negative, right? It's acting clockwise. Negative 500 times 1.5. And then all of the forces along the far side of the plate. So that's 3 times all of those TA, TC, and 200 pounds, just making sure that we're getting the signs correct. So my 200-pound force is also a minus 200 times 3 plus TA times 3 plus TC times 3. So I notice I can't solve this one yet, right? Because I have too many unknowns, too many variables. So I'll go ahead and set up our last one here, our moment, not about z, our moment about y equals 0. And for our moment about y, we're going to include our 200-pound force, our 500-pound force, TC, and TB, right? So I can set all of that up. And I say, okay, it's TB is negative. TB is negative since it would be acting clockwise around the y-axis. So TB times 4 minus TC times 4 plus now my 500 times 2 plus the 200 times 2. So now it's just a matter of solving the systems of equations, right? I have 3 unknowns, 3 functional equations. None of them give me a clear answer right away. I'm going to have to combine them in multiple ways to find out what my answer is. But that would be the setup for this one, right? So when I go through and solve this, I then get the following tensions, right? And that's just a matter of plugging and chugging into your calculator.